So now that we've spent some time working with the variance in a bit more depth, we've come to realize that there is a distribution for n-1 s squared over sigma squared. We've seen how to calculate the confidence interval for the variance. And now we're going to move on to a hypothesis test where the parameter we're testing is the variance. Now, these techniques for a hypothesis test should be really familiar to you. We've got so used to conducting hypothesis tests that a lot of it is going to make sense as soon as you see what's happening. What is different is the hypotheses themselves and the test statistic and potentially how we look up the critical value. All the other aspects of a hypothesis test will remain intuitive and work exactly how you would expect them to. Okay, let's quickly look at the context of this first example. So we're looking at a manufacturer of pistons for cars. Now a piston is an integral part of the engine of a car. The machine that produces these pistons finished the diameter of the piston to a specific size. Now the machine was set up so that it would produce pistons with a diameter that was normally distributed. And the parameters of that normal distribution are that the mean was set to be 60 millimeters and the variance was set to be 0.0009 millimeters squared. Okay, after the machine has been running for some time, a sample of 15 of these pistons are taken and the mean and the variance of this sample are calculated. The mean was found to be 60, so it was still 60, it was what was expected, but the best estimate for the variance was calculated to be 0.002. Now the manufacturer wants to know if the variance of his machine has increased. If over time, and due to the fact that the machine has produced multiple pistons by this point, he wants to know if it needs to be recalibrated. Has the variance increased or has it remained consistent with the value for which it was set? Okay, so that's the context we're working in. Let's try and get some specifics down so we can start this hypothesis test. Let's start how we'd start any hypothesis test, which is with the actual hypotheses themselves. The null hypothesis. Now we know the null is always trying to represent that everything is fine, everything is working as expected. In this case, the null hypothesis says that the variance is still, okay, this has come from me wanting to write 0.009 in the usual squared form that we use. The alternate hypothesis, well, that states, and the question is asked for us to test whether or not the variance has increased. So the alternate hypothesis says sigma squared is greater than 0.03 squared. Okay, what other values can we gather from the context of the question? Well, n equals 15. Immediately I know that v equals 14. Significance level, we'll take 5% as our significance level. So the sample variance was 0.002. Okay, so that's as much as we're going to need to move forward. What we're going to do now is that we're going to calculate a test statistic. The test statistics for this particular sample is going to be n-1 multiplied by s squared all over sigma squared. And we know that that follows a chi-squared distribution. So to find our particular test statistic value, we're going to substitute 14, 0.002, and 0.03 squared, and that gets us an answer of 31.1111. Well, how do we make a decision whether or not this is significant? What we're going to need to do is to calculate a critical value. So, just like we're used to, since we have a significance level of 5%, that means we want the critical value, a chi-squared score for the matching degrees of freedom that only has 5% exceeding it. So, in this particular case, degrees of freedom are 14, and that critical value is 23.685. Okay, let's just quickly put this onto a diagram. So the chi-squared distribution is non-symmetrical and it has positive skew. So I'll just try and show that in my diagram. And this is going to be my critical region. This is the 5% significance level critical region. Critical value. And our particular calculated test statistic is inside that critical region. So we know straight away that we have a significant result Because our test statistic is bigger than our critical value, we have a significant result. So we have evidence to support rejecting H0. And obviously we want to do that in context. There is evidence that the variance in the size of the pistons that the machine is producing has increased. Okay, evidence to suggest that the variance in the size of the pistons that the machine is producing has increased. All right, be careful just to include the extra detail there. Mark schemes very regularly insist on that extra detail. So hopefully as you look through this, there's lots of familiar aspects of the hypothesis test that you're conducting. But let's look at one more variation. What if we had a two-tailed test? In this particular example, we're told that a random sample of 12 observations is taken from a normal distribution with a variance of sigma squared. The unbiased estimate for the population variance is calculated as 0.015, and we've been told to test at the 5% significance level the null hypothesis sigma squared equals 0.025 against the alternate hypothesis that sigma squared is not equal to 0.025. Okay, so we've been given quite a lot in this question to begin with. We've been given the hypotheses, so let's just get those down. Obviously, we know immediately we have a two-tailed hypothesis test. So let's be careful when it comes to working with the significance level. We'll start with n equals 12 and v equals 11. Now, the significance level we know to divide by 2 instantly as soon as we're working with a two-tailed test, and that gives us 2.5% in each of the tails. We've also been given s squared to equal 0.015. Okay, let's just start with the critical value. The critical value is always going to come from the table, so we can just look up a chi-squared score in the table. But let's just get the parameters of the chi-squared correct. Degrees of freedom is 11, and we're looking for 2.5%. Okay, so this is going to be the critical value at the top end for the top tail, for the tail on the right hand side, and we're going to use 97.5% for the tail on the left hand side. So that gives us critical values of 3.816 and 21.920. Okay, so let's just quickly get that onto a diagram. And we know if our calculated test statistic is in that critical region, is in the shaded region, we're going to reject H0. If it's in between 3.816 and 21.92, then we're actually happy to accept H0. So is it in the rejection region or the acceptance region? Okay, let's calculate our statistic. n minus 1, that's 11, multiplied by s squared, all divided by sigma squared, 0.025. Our test statistic in this case is 6.6. Alright, 6.6 is right here. 6.6 is in the acceptance region. We do not have enough evidence to reject H0. As usual, let's just finish off with those last 3 steps: a comparison, a mathematical conclusion, and then a contextual conclusion. So, here's our comparison. 6.6 is in between those critical values. It's in the acceptance region, so we do not have a significant result. There is not enough evidence to reject H0. That's our mathematical conclusion, and in context, I'll just say that there's not enough evidence to suggest that there is a change in the variance. Okay, so one-tailed and two-tailed tests for the variance. The hypotheses are different, the test statistic is different, but the rest of the anatomy of a hypothesis test should remain the same and intuitive and familiar to you. Okay, try and get yourself a diagram so it's really clear on what are the critical values and where the critical region lies. A response like the one that I have on the screen is exactly what the examiner's looking for. Really clear, laid out well, and you're indicating exactly what you're calculating and what it then leads on to. Okay, so we'll stop there and you can take some time and get some practice.